Hello. In this example, we're going to look at determining the convergence of this alternating series. Now, per our textbook, we know we can say that the series converges if these three conditions are satisfied. And so what those conditions are is we have to show that all of these the non-alternating portion of this term, we can show that they're all positive, and we can do that by listing out the terms. So essentially, we just kind of ignore the alternating part, and we're going to look at the list of terms and make sure they're all positive. In this instance, we can see that in the numerator, when I plug in index values 1, 2, 3, etc., the numerator will always be positive, and the denominator will always be positive no matter what. So that's also good enough to say, because we have always a positive term over a positive term, that all of the terms are positive. The second thing we need to know how to deal with would be showing that the terms are eventually non-increasing. There's several ways we can do this. We can show that the nth plus 1 term is always smaller than the nth term, and that is for all little n, which are greater than or equal to big N being a integer. Or, my personal favorite is to just show that the derivative will always be less than or equal to 0. Remember, when we talk about this idea of non-increasing is a more abbreviated way to say constant or decreasing. Okay, so we're going to look at determining the derivative of this non-alternating portion here. And in order to determine the derivative, we would need to use the quotient rule. Remember, this is my u sub n term. So the quotient rule is u prime sum n is the bottom n squared plus 16 times the derivative of the top 10 minus the top 10n times the derivative of the bottom, which is 2n, all over the bottom, n squared plus 16 quantity squared. So u prime sub n, I have 10n squared, and then over here I'm going to have minus 20n squared. So I have negative 10n squared, and then I'll have a plus 160 over n squared plus 16 quantity squared. All right, when we look at this, are these terms always positive? Well, the denominator we can very clearly see is always positive. But what happens if I were to plug in n equals 1? What kind of number do I get in the numerator? In the numerator, I get a positive number. If I plug in n equals 1, I get positive 150. And a positive number over a positive number will always be a positive number. So what's happening here, we need, if we want to use the fact that the derivative is less than or equal to 0 to show that it's decreasing or constant, that means I need a negative number. So there's a lot of different numbers I could plug in. What if I try plugging in n equals 2, which would be the next index value? Well, if I plug in n equals 2, I have 40, take away negative 40 plus 160 will still be positive. So we start looking. Notice the definition, or our rules here, say it has to be eventually non-increasing. Where does that eventually non-increasing start? Well, if we plug in n equals 4, 4 squared is 16 times negative 10, negative 160, I end up with 0 in the denominator over a positive number, which is 0, which would mean at n equals 4, the function is constant. And what happens for larger indexed values? So if I said n equals 5, 5 squared is 25 times negative 10, I have negative 250 plus 160, okay? So that will give me that negative value in the numerator I'm concerned about. And we can say now that u sub prime of n is less than or equal to 0. Less than, the derivative being less than, means the derivative is decreasing. Equal to 0 means the derivative is constant, or the function is constant, I should say. And that is for all n values greater than or equal to 4. Now, you don't necessarily need to know that upside down A, but I like to use the shorthand notation because an upside down A is surely shorter to write than 6 letters for all. So the derivative is decreasing or constant for all index values beyond 4. So even though it is increasing for the first 3 terms, n equals 1, n equals 2, n equals 3, it begins to start decreasing. It is eventually non-increasing. Therefore, we can check off question number 2. And then the last piece we need to check here will be, is the nth term eventually approaching 0? And in order for us to do that, we would just look at the limit as n goes to infinity of 10 to the n over n squared plus 16. And we can recognize that because the degree of the numerator in this rational expression is linear and the degree of the denominator is quadratic, because the degree of the numerator is less than the degree of the denominator, we know that there's a horizontal asymptote at y equals 0, and that means the limit is equal to 0. Furthermore, if you didn't recognize that or remember your algebra rules about horizontal asymptotes, you could begin by trying to evaluate that, and that would be 10 times infinity over infinity squared plus 16, which is infinity over infinity and an indeterminate form. So I can apply L'Hopital's rule, and that means the limit as n goes to infinity, I'll apply derivative to the numerator, I get 10, derivative to the denominator 2n, and 10 divided by 2 times infinity is 10 divided by infinity, or 0. So we have verified these 3 conditions, and if the 3 conditions are satisfied, what can we say about this series? We know now that this series converges. So we know that this series converges by the alternating series test. But at this point in our series study, just saying something converges is not enough. We have to know if it converges absolutely or if it converges conditionally. And in order to do that, we come over here and we consider just the positive related non-alternating series. So in this instance, I need to determine a way to think about, is this series going to be convergent, just the positive related one? Well, there are different tests that we can use to check this series. One test that would be used, if it's easy to integrate and it passes the conditions of the integral test, would be the integral test. So when we think about the integral test has 3 conditions that must be checked. And those 3 conditions are that all of the terms are positive, it is continuous, and it is decreasing. Okay? So after the first 3 terms, we know this function is decreasing. We know it is continuous because the denominator can never equal 0. And that would be basically when you think about continuity, you're just thinking about the domain. So we know it's continuous. And then all of the terms are positive. When we're plugging these numbers, the numerator and the denominator will always be positive. So in that case, I can treat this as an improper integral from 1 to infinity, and I'll use the related function 10x over x squared plus 16 dx. Now this is easy to integrate. In this case, I can use u sub, and I will say let u equal the denominator, x squared plus 16. And if that's equal to u, du is 2x dx. So that 2 can move over to the left side of the equation. 1/2 du equals x dx. And then I'll also change my bounds. Before I do that, I'm going to go one more step here. Remember, when we're dealing with an improper integral, we need to use that limit notation. So this is the limit as b goes to infinity, the integral from 1 to b of 10x over x squared plus 16 dx. So now that I've applied that limit notation, I can rearrange my bounds. U equals b squared plus 16, and then I have u equals 1 squared plus 16, which I can simplify to 17. So working through this problem, I have the limit as b goes to infinity. My bounds are, the upper bound is b squared plus 16. The lower bound is 17. Now that 10 is a constant multiple, so I'll go ahead and pull that 10 in front. X dx is equal to 1/2 du, and the denominator is equal to that u value we chose. So x dx is equal to 1/2 du, that's this x dx, and the denominator was equal to u. Now, continuing through this problem, that 1/2 can come in front, and 10 over 2, or 10 times 1/2, is 5. So I have 5, the limit, as b goes to infinity of the integral from 17 to b squared plus 16. And then we'll have 1 over u du. Of course, this integral is very easy for us to integrate after we've applied that substitution. So I have 5 times the limit as b goes to the infinity, or goes to infinity, of natural log of the absolute value of u. And then my u values are b squared minus, or plus 16, b squared plus 16, and u equals 17. So we'll plug both of those values in, 5 times the limit as b goes to infinity of natural log of the absolute value of b squared plus 16 minus natural log of 17, and we don't need those absolute value bars there because 17 is a positive number. So now we're just faced with one challenge, which is determining what happens inside this integral when I plug in b approaching infinity. What happens to infinity squared plus 16? Infinity squared plus 16 just turns into infinity. And then what is the natural log of infinity? What's happening to that term? Well, we know our natural log graph is kind of shaped like this. And as x, the argument in the natural log of x, goes to infinity, where do those y values go? The graph goes up forever to positive infinity. So this term ends up becoming infinity, and I have 5 times infinity minus the natural log of 17. Infinity minus a constant is still infinity. You multiply it by 5, it is still infinity. So this integral goes to infinity, and we can say it diverges. And with a divergent integral, so the positive related integral over here, this is what we dealt with, the positive related series diverges. If the integral diverges, the series diverges. And so what does that mean about our original series we were dealing with? This original sum is conditionally convergent. So we wouldn't just say that it converges. It is conditionally convergent because the positive I'm sorry, I can't talk and write that word, conditionally convergent. And I would be looking for all of that work on your paper, okay? So because the positive related series diverges and the alternating series converges, this is a conditionally convergent alternating series. So again, what did we do here? You will check all three conditions to determine if the alternating series converges. If it converges, then we go and we apply a second test to the positive related series. And if the positive related series converges, at that point we can say absolutely convergent. But in this case, we used the integral test. Again, we checked those three conditions that allow us to apply the integral test. And we went through the integral test. We turned it into an improper integral. We applied a u sub. We solved. We found it diverges. Therefore, we say it is conditionally convergent. And that's it. Please let me know if you have any questions about this problem. I'm here to help, but I think this is a really great problem. It encompasses a lot of details of testing series.